Falcha, welcome to the MEER podcast. I'm Peter Downs, the director at MEER. I'm going to be hosting this podcast hopefully on a monthly basis. I'm joined by Dr. Ye Tao, who will be joining us and will be our educator on this journey. Dr. Tao received a doctorate at the Department of Chemistry at MIT in 2015. He also completed the research requirements for a doctorate in physics at Zurich. This was before running a lab at Harvard's Rowland Institute. But the more that Dr. Tao learned about global warming, the more he knew he had to refocus on that particular issue. To do that, he set up MEER, which is Mirrors for Earth's Energy Rebalancing. MEER is a non-profit organization focusing on surface SRM adaptation and mitigation research, and also climate education, which this podcast is obviously part of. We'll be discussing everything to do with climate reality, to feasible mitigation, to adaptation, the latest scientific papers, and obviously what's going on with the MEER project on an ongoing basis. If you do have any suggested topics you wish us to cover in the future, you can tweet us at MEERSRM on X. That's MEERSRM on X. Or alternatively, contact us through the website at neer.org. Like I said, the organization is a non-profit and we are funded currently by individuals, so any donations are always welcome to further our research and our humanitarian efforts. You can go to meer.org/donate. Okay, so this is the first podcast, so we're going to mainly focus on just getting to know Ye Tao, the person, and also look at some very basic scientific concepts. So we're not going to really dig into lots of the project or geoengineering at this stage. We will be covering those topics in upcoming podcasts. So yeah, you're 30,000 miles away from me. I'm in Belfast, you're in Freetown. So let's hope that the line holds up and there's no blackouts, but you're comfortable there, yeah?
Yeah, fair enough. I
Okay.
chose a stable location at a cafe, so please excuse the background noise.
All right. Okay, great. Well, listen, I just want to start off by the first thing we want to really know is a bit more about your own background. So, like where you grew up and how you were living in Canada and the US, I think, and studied maybe in Canada, and what got you interested in science in the first place, and why did you become a scientist?
Well, I was born in southwest China, where I spent my childhood, and up until like almost the end of elementary school. Then I moved with my family to upstate New York in the Syracuse area. That's where I first learned English. And for about a year and a half, I was on the school band and on the track team, and really liked the education system there. Then we moved to Montreal, Canada, where I did a double major throughout high school in music and the regular courses. And after that, went to Harvard for a biochemistry degree. But what really got me interested in science was my time in Montreal. I just stumbled upon a college physics textbook during one of the New Year parties at a friend's place, where one of the kids in that household was doing his undergrads in physics. So I got hooked by the first volume of 3, I think, and that was on mechanics. And that's how my interest in science got started. And then throughout the rest of high school in Quebec, we had a very good science education because it's structured differently compared to the rest of the world and rest of North America. After the equivalent of 11th grade, you have a 2-year junior college where essentially freshman and sophomore college courses are taught. So I had excellent chemistry and physics teachers who pushed us a lot. And it's during that time that I had a really solid foundation in chemistry and physics. And that's really what prepared for my future scientific career in college.
And how did you end up interested in nanotechnology?
So, okay, then the journey after high school, I basically participated in the chemistry Olympiad and won a gold medal for Canada at the end of my high school. And after getting into college, I focused on developing the practical aspects of myself as an experimentalist. So I spent most of my free time from class in the lab, in a physical organic chemistry lab, trying to understand the mechanism of a large organic molecule catalyzed reactions. And it's like detective work. You're trying to, through like indirect measurements, try to figure out the sequence of events that happen when different molecules meet in specific configurations and undergo a specific sequence of events in order for the atoms to be rearranged. So it became quite clear to me that existing technology for analyzing these chemical reactions and many other type of science remain to be further developed. So that's how I realized after undergrad that developing scientific instrumentation and the tools are critically important for enabling the performance of better scientific studies. So I decided to become an instrumentation maker and to learn how to make instruments to study and to take measurements of different things. So when the opportunity came to join Professor Christian Dagan to develop a new technique called MRFM, magnetic resonance force microscopy, which is a blend between MRI imaging and atomic force microscope. This technique would have the promise to deliver three-dimensional resolution images of minute particles of materials like viral particles, like semiconductor devices, and the whole range of small objects that are important for the functioning of modern technology and medicine. So when that opportunity came up, it was quite obvious to me that was the right direction to go into. So I spent about 10 years of my career in that field.
Yeah, and now obviously you're doing something quite different, but obviously a lot of that can be that experience can be brought into the field. How do you compare what you were doing then to what you're doing now?
The same training still comes in handy, even though we are operating under severe constraint in a lot of things. But I don't think it's a bad thing. As an engineer, you're supposed to be solving problems or using whatever material and resources are at your disposal. So there are several examples I can mention. One example are custom environmental sensors that we have developed ourselves using very affordable temperature and the humidity loggers. So these loggers individually, they can be sourced at roughly $20 a piece. And if you want to have a comparable systems that's a commercialized solution, they would cost you roughly 10 times that much, roughly $200 per sensor. Obviously, there's some disadvantage and advantage for each type. The commercial system enables you to integrate the whole measurement network more easily, so data taking is more automated. But a centralized system like that is also more prone to failure. If the central data logger gets inundated, as we have encountered in our system in New Hampshire, then the whole all the data are lost for that period. So in our more low cost, more individualized sensor setup, we have to download data from individual sensors more often. But in case of disturbances like fires or theft, not the whole system is impacted. We have partial data loss. So there's some advantages and disadvantages for each. But my training during nanotechnology, material science, and physical principles of sensing enables us to, have the tools and ideas to achieve commercial products, functions, and measurements.
Yeah, we certainly need that, and we certainly know how to work on a budget at MEER as well. So, listen, I want to kind of change tack a little bit and talk about environmentalism. And people like Derek Jensen and Lyra Keefe would say that environmentalism, has been captured by industrial lobbyists, and you're more likely to see environmentalists lobbying for wind farms and solar farms than saving wild nature these days. But how do you see environmentalism, and do you see yourself as an environmentalist?
Well, I was starting to see myself as an environmentalist, and actually, that development is rather recent. I would say it's probably after I really arrived in Western Africa and witnessing a very visible, receding of the forest line. That it's a very emotional feel when you visit a place that was lush forest just a few months ago, and then you visit second time, it's covered by charcoal pits and all the trees are gone. It's quite a emotional, shocking event. So I wouldn't say that I started this line of work as an environmentalist. I think I'm mostly a scientist and engineer, and but I do see it's very important. Environmentalism in my nations, because of our ecological and evolutionary ties to nature. It's what gives us life, what sustains us, and what has enabled our and guided our evolution as a species. So I think it's within each and every one of us, and the fact that not more of us are environmentalists is probably because of how we are raised as animals in captivity, having very little access to nature in a real sense.
Yes, I agree. People living in urban settings probably don't realize what's going on as much. Obviously, a lot of our focus is on trying to mitigate the worst effects of climate change on the natural world. But whilst doing that, we're also, building adaptation for people in desperate need of relief from thermal intolerance. Do you consider yourself a humanitarian also?
I think I would consider myself a humanitarian before I consider myself an environmentalist, but though I'm moving in, I've been moving in both directions. I think what really got me excited about this line of work, or really felt motivated or compelled to do this line of work, was starting I think at the late 2000s. I think there's a movie or a documentary called I forgot the name. Maybe it will come back to me. But the gist of it is that humanity has largely disappeared, and we have a repository of knowledge in some base in Antarctica or something like that. And as a scientist who started research quite early, at the end of high school, and basically devoting all my free time to doing meticulous scientific work, I understand how much sacrifice there is and how much difficulty there is in getting any single piece of data that's in the scientific and engineering literature. So if you look at all that work, it feels just emotionally very sad that we would be losing all this effort. Not only the science, but also the music, the art, all the culture, all the culinary traditions, all the different musical traditions of the world. It's just extremely sad to lose all that, because somebody have been there, and many people have been there to really spend their valuable time to develop that, to put their passion into work. So it's just really sad that we're losing not only the current generation, but human as a species, especially in that we are a continuation of our history, right? So what we're losing is not only the present living people, but also all the legacy of all the people before us. So I think that's initially what motivated me, or really sad me so much and depressed me so much to take the leap of faith and change my career path.
Yeah, it's very difficult for people to even comprehend that. So we know academic circles can be very specialized, and people have in-depth knowledge in specific areas rather than maybe seeing the broader picture. And you were probably one of those people as well. What would you say to critics that say you're not really a climate scientist?
Well, it depends on where they're coming from. I accept that I'm not a typical climate scientist who are experts, computer scientists, first and foremost. They're generally trained to code very well, and to run computer processes and automate data analyses. But I think what we're dealing with, the task at hand, is not to really to make the best representations of the Earth system itself, but rather the task now is to find the right reactions to unfolding catastrophe and catastrophic events. And there's no better simulation than Earth itself. Regardless of how much progress we can make, in the coming years to perfect our climate models, the Earth system will always be more exact than those predictions. And paleo climate data is there, and we do have a pretty good idea of how the Earth system responds, both in magnitude and in speed, to a certain extent, to the perturbations that we are subjecting it to. So from someone who's primarily an experimentalist, I don't really see the study of climate science in making these projections as really necessary to tell us what's ahead. In fact, I think they are a distraction, because all the major parameters we need to understand the future of the ecosystem can be derived from empirical science that include paleoclimate studies and also studies of forestry and also oceanography and coastal ecosystems and laboratory and mesocosm experiments on different ecosystems. And those have been completed already to an extent that enables us to foresee we cannot allow average Earth temperature to go beyond 1 degree Celsius roughly, because in no system that's been studied in the laboratory has there been observed positive impact if you go above average niche temperature by roughly 3 degrees Celsius, with the few exception of polar species where the rate limiting step is basically the freezing, operating too close to freezing. But for most of the Earth and the different latitudes, it's quite robust result that we cannot allow marine systems to go beyond 2 or 3 degrees Celsius. Terrestrial systems sometimes can exhibit a bit of tolerance depending on whether you're an animal or a plant. If you're an animal, you can perform what's called thermal refugia by either going to higher latitudes or climbing up the mountain. Actually, trees do that. Trees do not have the speed to move north or south, depending on which hemisphere you are, but they, relatively speaking, they are able to climb up mountain peaks. But all mountain peaks have a summit, and there's also other constraints, including pressure, oxygen levels, etc., and precipitation levels. So there's extent, there's limits to adaptation to thermal refugia. So all that is to say that empirical studies in the field are sufficient to make us worried about the future. And you couple that to empirically observed rate of warming in the past 30, 20 years, and we know we will be surpassing the 1.5 degrees pretty much anytime, within the next a few years, and the 2 degrees possibly before or by 2040.
Yeah, I agree. That science seems quite settled at this point. Just setting aside the crisis for a minute, do you actually enjoy the current field work, or do you miss the laboratory work, back in the comforts of Harvard?
Well, how should I put it? We are doing laboratory work on using controllable equipment, systems, instruments under ultra high vacuum conditions. It's a slightly more higher chance of getting to a state where your data is reproducible. So the cycle time from experimental conception, setup to data acquisition is slightly faster. When one is doing the type of field experiments that we're currently trying to do within real communities where people have to conduct their daily lives, it's a bit more complicated. There are factors other than how much care you take, and the factors other than the quality of instrumentation that you build or source or assemble. So there's potential for disasters. Maybe there's a rainstorm or snowstorm that inundates your experimental field. Maybe there's a fire that burned up your part of your experimental system. whether it be occasional theft of your equipment. So it's a different set of challenges, and generally the turnaround time for experiments are longer. So generally we are very exciting data, so one has to be more patient and more tolerant to such frustrations, and just understand that there are things that's out of our control in our best efforts. So that's why it's exceptionally important for the experimenters to not contribute ourselves to laws. And especially in environmental work, we are working with the seasons, just like in agriculture. So if you missed one heat season, then sorry for you, you have to wait until next heat season, wait for 2 months for a turbo pump to ship, then you can continue with your UHV high vacuum science experiment. So it's there's also the annual cycle to consider.
I mean, let's just get down to a few basics of science, really, because that's what this podcast is more or less about. So the word climate is used so much these days, but a lot of people probably don't realize exactly what climate is. So can you explain what is climate? What does it mean?
Before talking about climate, maybe we can talk about just what weather is. It's more or less, I would say, an instantaneous measurement of various outdoor environmental conditions. For example, you can measure outdoor wind speed, wind direction, precipitation rate, how much sunlight you're getting at this moment, and what's the cloud coverage looking like when you look up in the sky, and the temperature, humidity, the usual stuff. So when we talk about weather, it's generally more or less instantaneous measurement of these parameters over not typically longer than a few minutes to hours, right? Even over the course of a day, we say the weather can change. So that implies that when we're talking about weather, it's for measurements of such parameter conditions over relatively short periods of time. Okay, now if you take a time series of, or a matrix time series of all the ensemble of such measurements, and you do some statistics on them, say you have such data over a year, then for every parameter you can first of all plot a histogram of the parameters. You can choose to break up the year into monthly segments and plot histograms for these different months. You can choose to choose longer time scales, for example, over 10 years, and you take every January 20th of those 20 years and you do a statistic on those. So when you start to do those statistics over a longer time period, then you're starting to move into the realm of understanding the climate of a, say, in particular location. Obviously, you can also average or take statistic over different spatial locations, not only over the time coordinate. So I would define climate as the statistics of these outdoor environmental conditions, both over time and over space. And exactly like what period of time you analyze and what spatial extent you analyze depends on the application and the particular scientific question you're trying to address.
If I had a pound for every time a Twitter troll told me it's just the weather and nothing to do with the climate. But yeah, I just wanted you to develop that and just explain, how global warming is different from climate change.
Climate, just like weather, can also change. Climate is nothing but the means and standard deviation and the other statistical measures of the different environmental conditions, and they are able to evolve over time as a function of in the tilt of the Earth and the irradiance changes of the sun and other factors and natural processes feedback on planet Earth. And if you study the climate record, the paleoclimate record, it's obvious that the Earth system undergoes quite dramatic climatic changes on its own. Well, in the sense that without significant contribution from human activities. But the difference between natural climate change and global warming in recent decades to centuries is the rate, the speed at which these changes in the mean, in the standard deviation of the various parameters are taking place. It's not only the magnitude of the change, but over what time frame the same magnitude change takes place. That really matters. If we look at the change of the climate over the past a couple million years, and do a statistics on the rate of change, we can contrast that with the rate of change in the past 200 years. And those are by typically orders of magnitude for most parameters we care to look at, including average global temperatures and even local temperature trends, and also, of course, CO2 levels, which is the dominant driver for the ongoing global warming. So I hope that's clear. Correct me if you think I need to elaborate.
No, it's fine. It's fine. It just leads me into my next question as well. As I often hear arguments from climate deniers that the levels of CO2 in the atmosphere, they're so insignificant that it can't possibly be a reason for climate change. So what's the main evidence that indicates that climate change isn't a natural and that CO2 is the driving force?
Well, like one evidence that I sort of mentioned is the speed at which the temperature has been rising, and it's rising and it's lagging behind the CO2 concentration changes. So if the Earth system were given sufficient time, the temperature parameter and the CO2 parameter would track each other more exactly. So right now, given the current level of CO2, the temperature response is actually lagging behind what we observed in Earth's history. So that's one indication that in this pair of CO2, if they are somehow directly or more likely is the primary driver of temperature and the change. Or not us, but all the scientists studying these these topics. Before we know that the temperature is lagging behind CO2, it could also be that temperature is driving CO2 changes. So I think the major indicator is anthropogenic and actually really the orders of magnitude difference in the rate of change for these parameters compared to natural variation and natural climate change. And the second, that we can fairly well quantify how much emissions are due to anthropogenic burning of fossil fuels and also other land use disturbances. And these respond to, at least within a factor of 2, what we observe in the atmosphere, accumulation in the atmosphere, and also acidification of the ocean. So we can reconcile what we do with what we observe. So we understand where the atmospheric pool and ocean acidification pool are coming from. It's mostly coming from our consumption of fossil fuels and of other ecosystem biomasses.
Yeah, and I suppose the warming also has an impact on the permafrost and methane and feedbacks like that as well. So, yeah, some people point to, they'll say this is the coldest winter we've ever had in years. And you do see what's happening in the US and what happened in Texas a couple of years ago where, the polar vortex came right down. So why is this the case for some people and what's happening there whilst the planet is actually warming?
The fact that they're using a personal observation during a very limited period of time to say something about whole distribution is logically flawed, because climate is the distribution of such parameters over multi-year decadal timescales, and your personal observation taken over just a few days is but a few random samplings from such a large distribution. And that's point number one. And point number two is that we're looking at global averages and the regional averages. And there could very well be locations on Earth where the average temperature and average precipitation patterns will move in opposition to the global mean, to how the global mean moves. It's entirely possible. But that's not what we're talking about. We're talking about global warming. And we're talking about the average 2-meter surface air temperature increasing and or also sea surface temperature changing, and the total amount of stored energy in your system. And how that's excess thermal energy redistributes or distributes itself within the planetary system can most certainly show spatial heterogeneity, thus leading to these locally variable observations. That's why these local arguments over one season, 2 seasons are not really relevant.
But is the warming affecting the jet stream and the polar vortex?
I mean, it's certainly based on observations in recent years that there's a very remarkable destabilization of these atmospheric circulation events. And there's a phenomenon called polar amplification, which basically describes the fact that if you measured 2-meter air temperature over a different location on Earth, from the equator gradually north up to the pole, you measure very different rates of warming. So right now, globally average, we have roughly 1.5 degrees of warming, but at the pole in certain locations, we have up to 6-7 degrees of warming already. Whereas in near equator, it's maybe like 0.5 degrees. So the rates of air temperature warming is more pronounced as you go up in latitude. And that's a manifestation also of the fact that within the Earth system itself, thermal energy flows from the equator up to the pole. So all that excess energy that's gathered over the equator, over mid-latitudes, has to somehow, or part of it, have to flow and make its way up to the North Pole in order to be dissipated by IR radiation away from the pole eventually. And nature does it by different mechanisms, including by hurricanes, and also in atmospheric transport, but also by ocean currents. And these processes, when the atmospheric disturbance gets more, there's more energy instability and tendency for air to mix from lower latitude to up north, then you will certainly change the normal circulation patterns. And whenever there is a warm air moving north, there has to be compensating air moving south, because you cannot really create a vacuum anywhere very easily. So if there's like a very strong tendency for warm air from, say, somewhere in North Atlantic to move through the Bering Strait into the pole, then there has to be accompanying with that northward motion of air, a southward motion of cold air down, say, into the northeast of the United States. And that's what could be explaining the observation of more severe winter storms in certain locations in these northern latitudes as close to the pole. Right? It's also an indication that somewhere to your east there are strong currents of warm air rushing into the pole. Hence, you're getting this northerly wind down south.
Yeah, and it appears to be causing more storms as well. I mean, I looked at some data today for the UK, and since 2010, there's been a 300% increase in storms over the UK in just 14 years. So that's incredible figures. But yeah, so this you have firsthand experience now living in a very hot climate, and obviously it's getting warmer. So how is it actually affecting the people on the ground?
What's the most challenging thing about working and living in Sierra Leone? So typically we're operating well above 30 degrees Celsius during the day when it's, and that's for somebody in the States or the UK, it's 90 degrees Fahrenheit. And humidity levels are anywhere, 70 to 90% humidity. So you can imagine how hot that is. And when you're operating in such conditions, especially when there's, in addition to that, intense sunlight, one gets tired extremely easily. So it takes so much extra effort just to do very simple things. And one feels exhausted most of the time, and it's a real drag to perform daily activities and functions. It's not easy. No. People doing animal studies have been trying to also understand the impact of such high temperature conditions on the longevity. And there's a recent paper not too long ago, like last year, on using mice as model, and they were rearing mice at 2 temperatures one 20 degrees Celsius, the other 32 degrees Celsius, actually the temperature that we experience in Freetown. And what they observed was a 40% reduction in longevity of the mice reared at the temperature, and that has to do with cellular repair mechanisms and the many other several pathways that seems to be conserved all the time to mice to humans. So there's also interesting to trying to understand how that really impacts human longevity.
Okay, well, I'll just end with one last question for you then, because I want to talk about mental health really, and because it's a very tough subject for anybody to learn about what's going on with the climate predicament. And there seems to be increased anxiety in the younger generation as well, who are waking up to it. So with all that you know and all that you understand, and there's not many people that would understand as much of it as you do. I mean, how do you keep yourself, mentally sane and mentally stable?
Well, it goes to back to like my becoming what you call a humanitarian. I think after struggling with and coming to terms with the fact that all civilizations end and all mammalian species eventually go extinct, it becomes clear that it's futile to try to preserve, let's say, human civilization or even Homo sapiens as a species, billions of years into the future. That's simply not natural, right? All mammalian species have an expiration date of on the order of millions of years. That's 10 to the 6th. And within the time span, natural time span of our species, just like the natural span of a person, we can build different type of civilizations and groups of human beings. We have, experimented in our history with tribal organization, hunter-gatherers. We have dabbled in agriculture, and now we are, a fossil fuel enabled techno species that's really decoupled at the individual level from the natural environments. And most of these large-scale organized societies have a limited time span of a few hundred years. If you do a statistic on them, they normally follow a log normal distribution with a mean lifespan of roughly 230, 250 years. And that's roughly the age of our fossil fuel civilization. So in a sense, this set of living arrangements, in the words of Dr. Guy McPherson, is coming to its roughly its natural expiry date. So when one realizes that it's just part of the natural process, but of course in each incarnation of the civilization, it's maybe a slightly different mechanism, then one has to seek alternative meaning than the mere preservation of life, either at individual level, group level, or civilizational level. And for me, each person has to find their own answers. For me, it's about promoting well-being, giving people, sentient beings, the possibility to self-actualize, to experience the beauties of the world. I think for me that is the mission of a well-functioning civilization. And in spite of its short duration, this fossil fuel civilization, what it has managed above and beyond any previous civilization includes elevating the average life expectancy and the total number of sentient humans to an unprecedented level. So if we use different metrics for success, we are actually on pretty solid footing with respect to really optimizing a better existence for all the humans. Obviously, if all the social divides, all the inequities are continuing to exist, what's coming down the line would not be pretty and would definitely hurt the overall well-being and sensed lived experience of all the humans. But we have all the opportunity still to make that change. So for me and for many people working at MEER, I think we're hoping to change that from the grassroots to really decouple as much as we can human well-being and happiness and the root in fundamental biophysics of access to clean water, healthy shelter, and nutritious food, and try to decouple that from the financial system that has caused this decoupling between individuals and the natural world. And as civilization weakens, as our ability to organize large-scale transatlantic shipping and flights become more difficult, I think these localized efforts to really reconnect people to the biophysical flows would become more and more important. So it's important that in the remaining time that we have as a global species, that we fully develop the set of expertise to really reconnect with nature, with the land, and use whatever we have learned, smart tricks, let's say, to cope with more difficult conditions that we have created for ourselves in the past 200, 300 years. So these are things that help me on personal level to cope with the very sad realities for somebody yet to be primed with what's coming down the line.
Yeah, no, and it's keeping busy as well, and what you're doing as well is fantastic. And change is coming, whether we like it or not, and we need to prepare. Okay, so we're out of time. I want to thank Dr. Tao for his time and his excellent answers for this first podcast. We'll be back hopefully next month again, and we'll dive much deeper into the science and into the project and into the solutions, as people want to hear MEER as a solution and what we're doing. Thanks to everyone who tuned into the live stream and those listening on the recording. I hope you found the conversation useful and enlightening. Just remember, you can follow our developments as always on the website meer.org, or follow our X Twitter feed at MEERSRM, MEERSRM. Once again, MEER is a non-profit, and we really do appreciate any donations you can make towards our ongoing research and humanitarian efforts. To do so, just go to meer.org/donate. And if you go to our website, the front page, you can see our documentary of exactly what we're doing on the ground there. So thanks again, and slán go fóill.